Okay, let's go ahead and get started. Today what I want to continue doing is developing Feynman rules for spinors, for fermions. So last class we began our discussion of these Feynman rules. In particular, we considered what's known as Yukawa theory. So we're going to be studying the Feynman rules for Yukawa theory. This is a theory of a real scalar field, phi. So in the case of nuclear physics, this could be the scalar field whose excitations are pions, interacting with a spinor field, which in the case of the application to the strong nuclear force would be the protons or the neutrons. And these fields interact via a cubic coupling that I've just called Y here, the Yukawa coupling. And it's a coupling that allows one scalar to turn into two fermions. Okay. So for example, it would lead to forces between the nucleons that arise because of the interchange of one of these pions. And so the way that we study scattering in this theory is, well, first of all, for each external fermion state, we need to specify a spinor that tells us what the spin of that particle is. Okay, so so those are specified by a U or a V for the case of incoming particles, a U for an incoming particle and a V for an incoming antiparticle. And for outgoing particles, we need a U bar or a V bar. Okay, so let me just call this Dirac spinor an electron or a positron, okay, rather than a proton or a neutron. So the way that these Feynman rules work is that for an incoming electron, so that will be something that's coming in from the left. So that will give you a factor of U of P, where P is the momentum of the electron. An outgoing electron would be represented by a line coming out of the diagram on the right. So there you'll need a U bar. An incoming positron is denoted by a similar symbol, except with the arrow reversed. So the arrow is telling you what direction charge is flowing in this process. So if the arrow is pointing to the left, that means you have a positron. Pointing to the right, you have an electron, unless I got left and right mixed up. I have trouble sometimes. But in any case, the positrons require factors of V rather than U. Okay. And here, that blob that I'm drawing is just the rest of the diagram. Okay. And then, of course, you have incoming and outgoing scalars. Those are simpler. Okay. So, for example, those I'll denote by a dotted line. So this is an incoming scalar. This is an outgoing scalar. Okay. There, of course, scalars don't carry any spin or polarization or anything like that. So there are no extra factors in the diagram associated with that. We just need to specify their momentum. And then we have an interaction vertex, which allows a scalar to turn into a pair of a fermion-antifermion pair. Here you have to conserve charge at these interaction vertices, so you have to keep track of those arrows and make sure that they line up correctly. And as usual, this just gives you a factor of I times the coupling. There's a question? Oh, I'm sorry. I wrote the wrong arrow for the positron. Yeah. I told you I get left and right mixed up sometimes. Good. Thank you. Sorry about that. Hopefully okay, everyone's with me so far. Sorry about that. Okay. And then the rule is that you just construct you specify your external particles, and you construct all allowed Feynman diagrams, allowed by topology. Okay? And then you join, and for each internal propagator, well, you get a factor of the Feynman propagator for a scalar. So that's a dashed line giving you an I over k squared minus m squared. And for the scalar, for the fermion, you get the Dirac propagator that we worked out last week, or maybe it was on Tuesday. And of course, this Dirac propagator has an arrow, okay, telling you which direction charge is flowing. And we need to remember that this Dirac propagator is a matrix. It's a 4x4 matrix rather than a scalar. So the ordering of the Dirac propagators is important. And the important point, really, is that so when you write down the amplitude for the Feynman diagram, you need to multiply spinor indices by connecting up all of the little arrows. So what you want to do is you want to start at the left of the diagram, because that's where you're going to have a U-bar or a V-bar, and then you want to write down all of the various terms that appear as you follow that arrow until you finally get a U or a V with an incoming, for an incoming particle. Okay. Yes.
Yesterday you said start on the right with the U-bar.
Sorry, it's because I get right and left confused. You start on the right. You need to start with a U-bar, right? Sorry, my rights and lefts get a little confused. So just to give you an example of exactly what I'm talking about here. Okay, sorry. We're not doing QED yet. So this is the scalar version of Compton scattering. Okay. So let's say you had an electron and a scalar going in, and that's what your diagram looks like. So you would get a U-bar over here and a U over here, and then there would be a contribution that looks like a U-bar times a propagator times a U. And you would need to, this U-bar would have would be a U-bar of some momentum. This propagator would have some momentum associated with it. There would be some U's here, and then there would be a couple of interaction vertices. Okay, so hopefully that makes it clear exactly what we're talking about. Any questions? We're going to spend all day today working out examples of this. So if something is not clear, it probably will be. You look like you might have a question. Oh my God, sorry. Someday, my 4-year-old has approximately a better grasp on left versus right than I do. Yes. Good. Question.
You don't even have the excuse of it being late in the day.
I don't even have. Well, it's first thing in the day. If they had this class like a civilized time, say sometime between 1 and 2:30 in the afternoon, it would be perfect. Okay. Good. Any other questions? Okay. So that works for external spinors, okay. But for internal spinors, then what you just do is you trace over all of the various spinor operators, which will be propagators, along with the vertices. So, for example, if you wanted to study pion-pion scattering or Higgs-Higgs scattering, then you would have 4 propagators here that all get multiplied together, and then you would have to trace over them. Okay. And there's a factor of -1 for each fermion loop. This won't be so important in this course, but next semester when we start studying loops and normalization and stuff like that, these factors of -1 will be very important. Okay, let's see. Good. Okay. And as usual, we integrate over the each undetermined momentum. After enforcing momentum conservation at each vertex. Okay. And then the result is the scattering amplitude. So you put it all together, it gives you the scattering amplitude I times the matrix element. Are there any questions on this, on the general setup? Okay, so we, in principle, derived all of these rules over the last couple of classes. Today, all we're going to do is practice using them. Okay? But before I jump into that, is there any question, anything that's unclear? Okay. I mean, to some extent, we've spent this entire class working up to this point where we can write down the Feynman rules for quantum electrodynamics. And now we just get to apply it to all sorts of interesting processes. Any questions before I continue? Good. Okay, let me give you an example, just so that we can get some practice. Let's do E plus E minus to phi phi. So this would be the annihilation of an electron-positron pair to, okay, if this is, let's pretend we're, studying some particle accelerator. We have electrons and positrons colliding together. We want to create a Higgs pair. Okay? This is precisely the diagram that you would compute. Now, in the standard model, it's treated slightly differently because electrons are Weyl spinors rather than Dirac spinors. But this is basically the diagram, the computation that you would do. Okay? So if you think about it, so for each incoming electron, we need an arrow like that. For each outgoing incoming positron, we need an arrow like that. And if you think about it, so the only way, so we have no other fermions in the as incoming or outgoing particles. So that means that if you want to calculate at leading order, these two diagrams need to be joined up like this. Okay? And so at leading order, if you want to study the Higgs-Higgs production, then you would have two outgoing particles like that. So here we'll have a P1 here. So as we discussed last time, usually what we do is we keep the notation where momentum flows for fermions, for external particles, in the direction of charge flow. So we'll have to call that a minus P2. And then let's call the external Higgs guys K1 and K2, so that this is a tree diagram, so all of the internal momenta are going to be completely determined by momentum conservation. So this guy will have momentum P1 minus K1. And then there will be one other diagram, which is essentially the same thing, except it's sort of hard to jump over with a dotted line, but I think you know what I mean, except that the two external particles would be reversed. Okay, so what is that scattering amplitude? Well, it'll be the sum of two terms. So there are two interaction vertices, so you get two powers of the Yukawa coupling. And we just need to go ahead and write down the diagram using these rules. So so there's going to be a V bar associated with this guy and a U associated with this guy. So we've got a V bar of P2. And then we have, so for this that diagram on the left, we have a P1 slash minus K1 slash plus M over T minus M squared. And then for the second diagram, well, it's the same thing, except with a P1 slash minus K2 slash plus M over U minus M squared. And then we get a U appearing on the right. And here, as usual, T and U are the Mandelstam variables. And that's what you have. So a slightly more interesting example would be one where you study, say, electron scattering. So in this case, you also have two diagrams. So they would look like this. So these electrons are scattering via the interchange of a scalar. So for example, this is the amplitude that you would study if you wanted to describe the force between two nucleons coming from pion exchange. Okay. So this is the force that keeps all of the protons bound together in the nucleus of an atom. So here let's call these momenta P1, P1 prime, P2, P2 prime. And then you have to add in this other diagram where how do I want to draw that? Let me draw it so there's that other diagram. Okay. And that occurs with a relative minus sign because every time you interchange two external fermions, you get a minus sign because they anti-commute. The important thing to notice about this, which makes it a little more subtle than the diagram that we wrote down above, is that here we have two separate lines. Okay, we have two different lines, so they're going to be two different spinor contractions. Okay. So, for example, so again, we have an I times the Yukawa coupling squared. In the top diagram, we have a U1 prime bar U1 and a U2 prime bar U2 over t squared minus m squared. And then in the second diagram, we have the U1 prime bar contracted with U2 and the U2 prime bar contracted with U1, all over U minus m squared. Okay. And as usual, we get a pole in the scattering amplitude when the internal particle is on shell. Okay, in the sense that when t is equal to, sorry, there's no t squared there. When t is equal to m squared, that means that this internal particle is solving its equation of motion. Its momentum is equal to m squared, and so that's when you have a pole. And so, as usual, this is the idea, is that this is how you often detect particles in scattering experiments. So these are just a couple of simple examples in the case of the Yukawa theory. What I want to do now is tell you how we can generalize this to take into account photons and study quantum electrodynamics. And in fact, everything is going to be almost identical. So to generalize this, to include photons, that is to say, to study the theory of quantum electrodynamics. So we have to remember the action for quantum electrodynamics. So we have the usual kinetic term for the photons and the kinetic term for the fermion is modified to include the coupling between the fermions and the photons. So in particular, we need to use this gauge covariant derivative, capital D mu. Okay. So that means that that leads to a coupling term which looks like E minus E times A mu psi bar gamma mu psi. Remembering our slash notation, that when you take a vector and you put a slash through it, that means you contract the mu index with gamma mu. Okay. So this leads to another interaction vertex, where now a photon can turn into an electron-positron pair. So the Feynman rules are just as in Yukawa theory, except that now the propagator for the photon is a little bit more complicated. It has two indices. And we need to include polarization states corresponding to the external photons. Okay. So we need to account for the spin of the photon. So in particular, we now have a photon propagator. So this is what we spent some time deriving when we were studying scalar QED. So that propagator is just equal to the metric. So you need an index for each one of the ends of the photon propagator, because the photon has a vector index. And there's this gauge-dependent term. So here, in our psi gauge, it has a general form where you add to g mu nu over p squared. So almost always in this course, we're going to set this equal to 0 by going to Feynman gauge, where zeta is equal to 1, or psi, whatever that thing is called. Today what I'd like to do is, just for a couple of examples, I'd like to keep that factor there, just so that you can see that it's actually not going to matter, and that our scattering amplitudes are going to be gauge invariant. Okay. This is something that we checked a couple times when you're doing scalar QED, and we'll just see that exactly the same thing happens here. Okay. It was guaranteed to work because the action that we wrote down was gauge invariant. But you know, it's always nice to check that explicitly. So I'll keep that term in for now, and you'll be able to see explicitly when we start calculating things that actually, once you include everything, all of the factors, all of the terms involving the gauge-dependent pieces of the propagator will not matter. Okay. But when you actually do calculations, you know, unless you're specifically trying to check gauge invariance, you could always set it equal to 0. So for every internal photon, for every external photon, so this is some sort of incoming photon, this gives you a factor. So if the photon, say, has momentum p, then this gives you a factor of the polarization vector epsilon. So this would be for some incoming photon. And then likewise, you'll get a factor of epsilon star for an outgoing photon. And we have an interaction vertex. And the thing, sorry, there was a question? Okay.
I want to ask you about if we want to consider the generating function for
Mm-hmm.
QED, the sources for the photon field would be some vector J nu, right?
Absolutely.
And these vectors would be the psi bar gamma mu psi. Or
Okay. Yeah. Did we derive? How did we derive? I don't think when we derived the propagator for the photon, I didn't do it that way. Okay. But of course, you could. So you could, when you study the generating function for the photon, introduce a source for the photon. The name that we give that source is a current. Okay. And so if you were to generate, so for example, I mean, that's a good question. So for example, if you were to write down the generating function of a photon, say in scalar QED, you would have the integral d phi, dA, d psi bar, and then you would include the action, so you would get, well, let's just write it out explicitly, d4x minus 1/4 f squared plus psi bar I d slash minus m psi. So that's the usual kinetic term. And then in this interaction term, you would have E a mu, and then you would introduce a source, j mu plus psi bar gamma mu psi. Okay. So this would be a source in addition to the one that comes just by the coupling of psi to the gauge field, and then you would have these various eta psi terms. Yeah, I mean, when you write down the source, when we say a source, it's an external source. Okay, that's a good question. I mean, I suppose that, there are many different ways of deriving all of these various things. I suppose when I did the gauge field, I didn't use the path integral point of view. When we come back and do gauge theories next semester, we are going to take the path integral point of view because there's some subtleties involving gauge invariance that you can really only sort out if you kind of think about it from a path integral point of view. I probably just didn't want to deal with all of the indices. Okay. But of course, it's completely equivalent to what we did. Yeah. Yeah, I suppose I could have taken a unified perspective and I don't know. I sort of like to mix things up and give different sorts of presentations because when you derive a propagator, you can either do it by doing an explicit calculation involving raising and lowering operators, by solving for the Green's function, or by doing a path integral. Okay? All three of those are completely equivalent. Depending on my mood when I'm writing up my notes for a lecture, I choose one of those derivations. Okay? Yes. Whichever one I understand. Yes. Good. Other questions? For example, I think I did the second when we derived the propagator for photons. But it would be actually a very good exercise for you to go ahead and do it the other two ways. That would be a great exam problem. It's probably in the book, though. Okay. Any other questions? Good.
Yeah, just about the gauge, and I think
Mhm.
you talked about this back when this was first presented, but are there any other useful gauges to work in?
Absolutely. In calculating Feynman diagrams, Feynman gauge is probably the most useful. Sometimes people also use what's called unitarity gauge, where they take zeta to infinity, or psi, or whatever that variable is called, to infinity. You always have to be a little careful when you do things like that. People also, there's a zillion gauge choices out there. And at the end of the day, for the purposes of Feynman diagrams, you just want it to be as simple as possible. And obviously, Feynman gauge is the simplest. But when people do other sorts of calculations, sometimes people will use, I guess it's called temporal gauge, where they set A0 equal to 0. Okay? And in that case, you only have spatial degrees of freedom for A. And that can be very useful. But it's also, understanding how to do the path integral and understanding so when you go to a gauge, there are okay. I don't want to get into it, but there are things that are kind of confusing about that, and I think there are various things people try and do in Yang-Mills theory and gauge theories by making various gauge choices, and there are all sorts of subtleties when you involving gauge choices when you quantize the theory, and so it's something that has to be done sort of carefully. But the answer is yes, there are many different useful gauge choices.
Fixing a gauge when they're looking at some other aspect of the problem that
Absolutely. So, one of my favorite examples is that there are people who try and solve strongly coupled Yang-Mills theory not using scattering Feynman diagrams because it's strongly coupled. The coupling is strong. So, perturbative expansions involving Feynman diagrams don't work. Okay. So what do? People write down the Hamiltonian and they try and quantize it. Okay. And they try and find its spectrum. That is a very, very difficult problem, but many of the approaches involve very clever gauge choices and things like that. So yeah. Right. Good. Other questions? If you were doing lattice calculations, for example, there may be very clever choices of gauge associated with that you might want to use. Yeah. Good. Okay, now this interaction vertex.
I just one more question, and that's about the minus sign that you get when you exchange fermion lines.
Mm-hmm.
Can you show, if you can do this quickly, just how the minus sign pops up in, say, looking at the interaction Hamiltonian and explaining that out in
Sure. I mean, the interaction Hamiltonian literally has a psi bar psi, okay? And you expand the psi bar and the psi in terms of raising and lowering operators, and it literally comes because those raising and lowering operators anti-commute with one another. Is that,
Yeah.
or did you want more explicit than that? I
No,
mean,
I remember actually going and working this out once. I just couldn't remember.
okay.
off the top of my head where
I think that, well, okay. I mean, I think that roughly speaking, you have, if you think about it, just by literally writing out the Hamiltonian, okay. So for example, you might have a Hamiltonian. The interaction Hamiltonian would be something like psi bar psi times whatever field it's coupling to. And then you would have you would write this in terms of raising and lowering operators. So this would be like an A plus a B dagger and an A dagger plus a B times phi. And then it comes from the fact that all these various different A's and B's anti-commute with one another. And so if you then want to try and calculate, say, the scattering amplitude, you have some external state. So let's say, I don't know, you've got an external, you want to calculate, so schematically, let's say you want to calculate the contribution to something with an incoming electron and an outgoing electron. Then you would have an A dagger on the right and an A on the left. And then, I guess you said if we want multiple particles, let's call those A1 and A2, A3 and A4. And then if you permute the A1s and A2s, those things anti-commute until you'll have various signs that appear. Okay. I'm using this interaction Hamiltonian language, which is actually not how we've derived these things in class. We've taken more of a path integral approach. But maybe in your textbooks, I don't know. Like, I don't think in Schwartz I guess he does give a derivation in terms of the interaction Hamiltonian. Peskin and Schroeder does it as well. I haven't really been using that approach, but you should be able to see it that way. In the in the path integral approach, it arises because you're taking these derivatives of these generating functions, and it's a derivative with respect to an anti-commuting variable. In the interaction approach, it's because literally you're studying states, the expectation value between states that are created with these fermionic oscillators. Good. Any other questions? Okay, this was just an aside. Okay, so now this interaction vertex in quantum electrodynamics, well, it just comes from this coupling term here. So you have minus IE times the coupling, which is, minus I times the coupling, which is E times gamma mu. Okay. So remember that we have a mu index here, and we have a pair of spinor indices that we usually call alpha and beta. So if you wanted to write out all of the spinor indices, I guess you could write them like that. I'm not being terribly careful about whether my Dirac indices are raised or lowered. The reason being that we usually don't like to write out the Dirac indices. So usually we'll just write it like this. Whereas we do usually write out explicitly the vector indices. Because if you don't write out any indices, then it's very difficult to tell what you're doing. Okay. But the important point to remember is that this is actually an interaction vertex with 4 times 4 times 4, 64. So 64 possible numbers, right? It's got 4 indices, 1 vector index, and 2 spinor indices. If you actually wrote this all out in complete, you certainly don't want to write everything out explicitly. You want to write out as few indices as possible. Otherwise, this interaction would contain 64 terms. Okay. So, so as usual, we suppress the spinor indices when we can. Okay. Okay, so now we can go ahead and start computing things. So are there any questions before I start diving into some QED computations? Now, the computations are really not going to be, that much harder than anything that we've done in this class. It's just there's more indices to go along. Okay. So let's consider the following scattering process. Okay. So let's consider, actually let's make life a little bit more interesting. Okay. So let's consider the annihilation of an electron and a positron. And what I want to do is have them annihilate and form not an electron-positron, but rather a mu plus and a mu minus. Okay. So what is a mu? What is a muon? Okay. So a muon is exactly like an electron, but heavier. Okay. So if you want to describe the theory of electrons interacting with muons, that's just a generalization of quantum electrodynamics to include two different fermion fields, one of which you call the electron and one of which you call the muon. And the mass of the muon is much bigger than the mass of the electron. So if you want to, so this process where an electron and a positron annihilate and form another pair of particles is certainly one of the most important processes in quantum field theory. It's the basis for all accelerator physics, basically, things like this. You may or may not be colliding electrons together, but you're colliding something together. So the scattering amplitude looks like this. So here we have two incoming electrons and two outgoing muons. So let me just give a name to the various momenta. So I'll call K the momentum of the internal photon. So let's just go ahead and write that down using our Feynman rules. Okay. So we get a factor of minus IE coming from, or let's just say minus IE squared coming from the two interaction vertices. And so let's start here and then trace through that spinor line, trace through that line, and you'll get a V bar of P2 times gamma mu times U of P1. Then you have a photon propagator, so you get a minus I times G mu nu, and just for fun, I'll include that gauge-dependent term so that we can see that it's going to cancel out. So there's the photon propagator. And then we have the final interaction vertex, which is a gamma nu. And that's going to be sandwiched between a U bar of P3, gamma nu, V of P4. Just following through, just tracing that spinor line. Okay? Just following this line here. Okay. I mean, as long as you draw the arrows, there's almost no way that you could do this wrong. Okay? As long as you draw the arrows, and remember that what you have to compute is a scalar at the end of the day, there's almost no way of writing down the wrong expression. So for example, the way that I wrote down this expression here, I started with the P3 guy here and wrote down the U bar associated with that. And then I had this gamma, so I had a U bar of P3 associated here, and then a gamma nu from that guy, and then I had a V coming from this guy. I could have also started here and gotten a V bar gamma nu U, okay? But V bar gamma nu U is the same as U bar gamma nu V. Actually, no, they're complex conjugates of one another. Sorry, that's what you would get if you complex conjugated the diagram, right? So you need to remember the rule that you need to start with the outgoing arrow. I guess that's the best way of saying it. Yeah. Okay, good. Are there any questions? Yes.
So the first vertex, P3,
Yes, minus P2. I should probably write it there. But it doesn't actually depend. So there's no actual P2s that appear in this. Yeah.
Question is, if we impose momentum conservation of those vertex, then how we strike K in terms of P1?
Well, I mean, you just need to be.
K is just
Well, let's put it this way. Well, I mean, you could write if you want to take your. Should I say this clearly? I mean, if it's helpful, we could just draw separately the momentum arrows, separate from the charge arrows, okay? And then this would be P2, okay? But we write it as minus P2 if we want to have the momentum arrows pointing in the same direction as the charge flow arrows. So for example, if we wrote it like that, then K would be P1 plus P2.
Are we going to see an example that the minus P2 is up
Um,
the minus sign at
I don't think so. Yeah. Yeah. Okay. So let's go ahead and stare at this for a little while, okay? Because, in fact, we can simplify this considerably. Okay. So the first thing that we should notice is that, so the first thing that we want to see is that actually this term drops out. So how can we see that? Well, we need to use the fact that these U's and the V's that are appearing here all need to solve the Dirac equation in momentum space. Okay. So remember that P, so U is annihilated by P minus M, and V is annihilated by P plus M. Or did I get the sign wrong there? Is that right? That's right. Okay. U is annihilated by P minus M, and V is annihilated by P plus M. So, or we could rewrite that as V bar is annihilated by P plus M acting from the left, just by taking the conjugate of that equation and multiplying by gamma 0. So if you look at this term here, what do you get? This gamma mu contracted with that k mu gives you a k slash. Okay. What is k slash? K slash is P1 plus P2. And so if you put it all together, the P slash, the K1 slash, sorry, the P1 slash acting on the U here will give you a factor of minus M, and the K2 slash acting on the V here gives you a factor of plus M. So the whole thing cancels out, and the result is gauge invariant. So that means that you can simplify our expression a bit. So what do you get? Well, you get E squared over S, otherwise over K squared, otherwise known as S, the Mandelstam variable, and you get V bar, I'll just use a subscript to denote the P2, so V bar 2, gamma mu, U1, times U bar 3, gamma mu, V4. Oh, and there's a minus I from there that I forgot. So you get I. Okay. So mu is equal to that. M is equal to that. Okay, so that's the scattering amplitude. If we care about the spins of the external electrons and muons, then you just insert the expressions for U and V corresponding to the spins of those particles. So in the exercise, one of the exercises you'll do next week, that's precisely what you're going to do. I don't know if it was this process or if it was a slightly different process. I think it might have been electron muon scattering rather than E plus E minus annihilation. But that's exactly what you're going to do to compute these various terms. Okay. So instead, what I would like to do is let's just consider the case where we don't actually care about the polarizations of the various spinners. Okay. So let's just pretend that we don't care. So that means that we need to average over all possible spin states. Okay. So we need to average over the possible spins of the incoming particles and sum over the spins of the external particles. Sorry, sum over the spins of the outgoing particles. Okay. So I don't know what the spin of my internal particle is, of my incoming particle is, so I just average over its possible values. I don't care what the spin of my outgoing particle is, so you just sum all possible spins that it could have. Okay. And so in that case, what we're going to do is we're going to get a simplification, just like the sort of simplification that you got when you studied electromagnetism and you summed over the polarizations in one of your problems. And we need to use the fact, which I think you derived on one of your problem sets, that, for example, if you sum over spin states of a V times a V bar, you just get P slash minus M. And the sum over spin states of U times a U bar is P slash plus M. So this is something that we already used earlier when we calculated some propagators, I believe. Did we use that? We used that earlier when we calculated some propagators. You derived this, I think, in a problem set, and now we're going to see why it was that you derived that. Okay. But were there any questions? Yes.
Isn't average and sample same
Well, they differ by a factor of 2, right?
thing? Yeah.
Okay.
But, why we don't sum of these possible spins for the income?
Well, you do some. Okay. Let me put it this way. I mean, you do some, but you should divide by a factor of. So, how can I say this? If you don't know what the initial possible state is, then there's a 50% probability that it's one state and a 50% probability that's the other state. So you take 1/2 of the amplitude with one possible spin plus the amplitude with the other possible spin.
So you don't average for the outgoing also because you want the
You just want the total number of muons that comes out, say, at a particular angle. Okay. Sorry, is that more or less clear?
Yeah.
Okay. The battery is about to die. Any other questions? Okay, good. Okay, so we have here an expression for the scattering amplitude. So let me just rewrite it here. So it was E squared over S. Is there an I or something? No. E squared over S, V bar 2, gamma mu, U1, times U bar 3, gamma mu, V4. So what we need to do now is multiply this times its complex conjugate. Okay. So in order to take the complex conjugate, what we need to do is remember that, so when you take the complex conjugate, say, of this first expression in parentheses, you need to take the adjoint of the gamma matrix, and remember we either showed in class or maybe you proved on a problem set that gamma mu dagger is the conjugate of gamma mu by gamma 0. So that means that if you want to take the complex conjugate, say, of an expression that has, say, a spinner times gamma mu times another spinner, so what is that? Well, you just take the dagger of all of the various spinners that appear here. So you get a psi 2 dagger, gamma mu dagger, psi 1 bar dagger. And remember that bar is just taking the dagger times a gamma 0. Okay. So, psi bar is psi dagger times gamma 0. So all of the gamma zeros work out so that complex conjugation just reverses the ordering of the psis in this spinner combination. Okay. So that if you want to compute the absolute value of this guy, you get e to the 4th over s squared. So you get this quantity in parentheses here times its complex conjugate. You get a V2 bar gamma mu U1 times its complex conjugate, U1 bar, let's call it gamma nu V2. And then we have a similar expression for those other two guys. So you get a U3 bar gamma mu V4 and a V4 bar gamma nu U3. Okay. And I have to be careful here not to muck up my vector indices as well. Okay. So I was careful to write separately the mu and the nu indices. Okay. The mu index came from this guy here, and the nu index came from its complex conjugate. Is that clear so far? When we spin sum and average, when we sum over all spins, and then average, so when you average, well, we're squaring, so you'll get a factor of 1/4. So what do you get? Well, let's see, you'll get... So what we need to do is we need to use these two expressions that we wrote down above. So there are actually 4 different spins that we're averaging over, okay? The spins of particles 1, 2, 3, and 4. When you sum over the spins of particle 1, that u bar u is going to turn into a p slash plus m. And you could also, here, you could also be a little clever. Here, let me write this all out a little bit more explicitly rather than trying to explain it in words. So let's look at this first expression right here and sum over spins. So let's call the spin of particles 1 and 2 S1 and S2. So what do we have? We have a V bar 2 gamma mu U1 and a U bar 1 gamma nu V2. So that quantity there is a scalar. Okay. But I could also write that as a trace, or a trace over a spinor index of a 4x4 matrix, which is the sum over S1 and S2 of V2, V2 bar, gamma mu, U1, U1 bar, gamma nu. So if that's not obvious, just think for a bit about exactly what a trace means. So if you have a matrix and you're taking its trace, That means you're contracting its two indices together. The traces are cyclic, okay? So I could always take this V2 and move it over here, and then you would just be taking the trace of a number, and that would give you this expression here. So is that a little confusing? Okay. So let's just if that's a little confusing, just write out all of the spinor indices explicitly. And I think that so if you want a slick way of saying that, you could just say that this is a number, okay? Any number is equal to its trace, and traces are cyclic, okay? So you can always move something from the end of the trace to the beginning of the trace, or vice versa. And then you get an expression like this. And then we can use our friendly polarization sums. So the sum over spin over S2 of V2, V2 bar. So let's just write that out a little bit more. Well, the sum over S2 of V2, V2 bar is P2 slash minus M. And then we get a gamma mu. And then we get a P1 slash plus M times gamma mu. Yes?
So can you tell us what the argument of the first sum is? The matrix.
The first sum. Which sum? You mean the one that's underlined? This V2 gamma mu U1, U1 bar, gamma nu V2. This is this term right here. Okay, it's the first term appearing in the square of the scattering amplitude. We now need to average over the spins.
Okay, so for every mu and nu, this is a scalar.
That's right. Yeah. So what I'm doing is I'm rewriting a scalar as a trace of a 4x4 matrix. So right here we have a scalar. This guy's a scalar. And I'm rewriting that scalar as a trace of a 4x4 matrix. That's what I'm doing right here. And I'm doing that because it lets me reorder the V's in order to actually perform these sums over spins. Okay. Don't worry, you'll do this on the problem set for next week. So if this is not, yeah. Okay. But I'm helping you out here. Okay? Is that clear, more or less? So, I mean, writing, okay, what could be simpler? Writing the writing a number as the trace of a 4x4 matrix. And then we get to use, using the cyclic property of the trace is your friend. Okay, the fact that you can always cyclically reorder matrices inside a trace is incredibly useful in situations like this. Okay, so that means that when you write down the summed and averaged scattering amplitude, if, for example, you want to calculate a cross-section, a scattering cross-section, as a function of the center of mass energy and the angle at which you're doing the scattering process, then you get e to the fourth over 4s because of that factor of 4s squared, because of that factor of 4 out front, and you get the product of two terms. Okay, there's this first term that we just computed, so P2 slash minus M gamma mu, P1 slash plus M gamma nu, and then a second term coming from this guy right here, where you do the exact same manipulations. So you get a P slash 3 plus M coming from the U3 times the U3 bar summed over the spin of the third particle, and then a gamma mu, and then P slash 4 minus M times gamma nu. Now, there's a lot of places where you can sort of make mistakes here. You have to make sure that you keep the ordering of all of the spinor matrices the same, the 4x4 matrices the same. You also have to make sure that all of the various indices get contracted in the right way. You know, when I was preparing this lecture, I had to go through a few times and make sure I had everything contracted the same way. But at the end of the day, you get a expression for the scattering amplitude, and hence the cross-section, that depends only on these momenta. these gamma matrices are just, these are just things that, these are just constants. And so, in principle, you could just go ahead and compute these traces all out explicitly. Okay. And in order to simplify this, what we're going to need is some way of simplifying expressions involving traces of products of gamma matrices. As you can hopefully guess, whenever you calculate sort of scattering amplitudes in quantum electrodynamics or in general for any theories with spin, if you're summing over all of the spin indices, at the end of the day, the only thing you can ever end up with is the trace of a product of gamma matrices. And so in order to simplify this further, we just need to understand how to manipulate these guys. Did I actually in a problem set have you calculate the traces of various gamma matrices? I know I had you do some gamma matrix manipulation, but I don't know if I had you do that. Okay. So it's rather straightforward. Okay. So for example, can anyone tell me what the trace of gamma mu is? It has to be 0, right? Gamma mu is a 4x4 matrix with a vector index. If you take the trace over that 4x4 index, it has to be a vector with one index, and there's no Lorentz invariant vector with one index. Okay, there's no momentum appearing here, so it has to. So, by the isotropy of space, by Lorentz invariance, this has to be equal to 0. Okay. Similarly, if you take the trace of gamma mu, gamma nu, well, you know that it has to be proportional to the metric, because that's the only two-index object that is Lorentz invariant. And the coefficient you can compute either by choosing your favorite basis and just computing one example of this and checking what the coefficient is, or you could use the fact that gamma mu, gamma nu is equal to 1/2 of the anti-commutator of gamma mu with gamma nu, and then use the cyclic property of the trace to relate that to the trace of gamma mu, gamma nu. And using the Clifford algebra, you'll get a factor of 4 there. Similarly, the product of any 3 gamma matrices, or indeed the product, as you can see where this is going, of any odd number of gamma matrices has to be equal to 0, because there's no 3-index object that is Lorentz invariant and has no spinor indices. And finally, as you can see, all of the quantities up there are going to involve traces of up to 4 gamma matrices. And this, now, so if you think about it, there are only 3 possible Lorentz invariant objects that you can form with 4 indices. So they have to be products of metrics. And then all it is a matter of determining the various signs. Okay. So rather than making you derive it, I'll just tell you what the answer is. So this you can prove using the Clifford algebra. You know that has to be the sum of these 3 possible terms. And so it's just a matter of, for example, choosing your favorite basis and computing this in 3 different cases to fix the 3 coefficients. Or you can prove this using some various manipulations of the gamma matrices. So for example, you could write down this thing, and then you could start contracting indices. And when you did that, you could reduce it to if you contracted, say, the rho and the sigma index, then you have to be able to reproduce this expression. Okay, so that fixes one coefficient. And then contracting the various other coefficients fixes the remainder of the coefficients. And then there are various other explicit formulas that you can derive. I'm sure there are cases, where you might need 6 gamma matrices. Okay. I don't know if we'll do them in this class, but I I think I've done that in the past. I think I needed it once. Okay. So you can then go ahead and simplify the expression appearing in the spin averaged scattering amplitude. So what do you get? Well, there's one term that involves only a gamma mu gamma nu times m squared. So that's easy to find. So you get an m squared times the trace of gamma mu nu. So minus m squared times the trace of gamma mu nu, gamma nu, which is 4m squared g mu nu. Okay. Then there are the terms linear in M that involve a trace of 3 gamma matrices that are equal to 0. And then there are the various terms that have no powers of M that involve a trace of 4 gamma matrices. So let's just write these down. So you get a factor of 4. And then there's it's P2 slash gamma mu, P1 slash gamma nu. So that gives you a P1 nu, P2 mu, if I did that correctly. From the first term, let's see. That's right. And then the second term gives you a minus P1 mu, P2 nu. And then the third term gives you plus P1 dot P2 times G mu nu. Hopefully I did that correctly. Is everyone with me so far? Yeah. I mean, the rule being that this first term is you contract the first two indices, the mu nu index and the rho sigma index. So that was why this P2 got a mu index and this P1 got a nu index. In that second term, we contract the first and the third index. Oh, okay, so that's this term here. So that gets a minus sign. Sorry. And this term gets a plus sign. Sorry, I was doing it in the wrong order. So in in this term, the first and the third index get contracted, so that gives you a P1 dot P2, and then you had a G mu nu. And then in this last term, the first and the fourth indices get contracted. Okay, and so if you write out the spin-summed correlation function, or spin-summed scattering amplitude, then you just get a product of two terms like this. So you get a 4e squared, sorry, 4e squared, okay, e to the fourth, 4e to the fourth over s, okay, because there'll be two factors of 4 coming from these spin sums. And what do you get? You get a P1 mu, P2 mu, P2 nu, plus P1 nu, P2 mu, minus P1 dot P2, G mu nu, minus m squared G mu nu, all times exactly the same thing with 3 replaced with, so 1 replaced with 3, 2 replaced with 4, and I guess I haven't been very careful here. So these were the internal particles, so they were the incoming particles, which were electrons. Okay? So that's the mass of the electron here. And the other particles, the 3, 4 particles, were muons, so that m needs to be the mass of a muon rather than the mass of an electron. And then we could go ahead and work this all out explicitly. Okay. How how explicit do I want to be? Okay. So then there's a bunch of algebra. So at this point, it's just a matter of doing some algebra. So I'll just write down the answer for you. Okay. You're going to derive a very similar answer on your problem set in a slightly different context. So the answer expressed in terms of the Mandelstam variables takes a relatively simple form. I mean, you know, simple really is a relative concept. And in quantum field theory, when you do these calculations, you begin to develop a different notion of what simple means. So this is the answer that you get. I think in your problem set, I asked you to derive this answer for a slightly different scattering process. But I allowed you to consider the case where all of the masses are very small so that you can neglect all of these terms. Okay, so the computation you have to do for your homework is a little simpler than this. But one can work it all out explicitly. It's all completely straightforward. And then from this, one can extract, for example, the cross-section say d sigma by d omega, which will tell you the amplitude for, say, an E plus E minus pair. So let's say we want to work in center of mass frame, to come in and sort of collide, and then out pops a mu plus mu minus. And as usual with 2 to 2 scattering, there are two kinematic variables. So there's a scattering angle theta, and there's an energy of the scattering process. Okay. Now there are many different ways you can characterize 2-2 scattering, many different variables you could use. You could use S and T, T and U. You could use, I don't know, other combinations of momenta. But conventionally in scattering processes, we often work in center of mass frame. And we could write this as a function of the scattering angle and the energy in the center of mass frame. And that's just a matter of going through and writing down the explicit expressions for S, T, and U in terms of theta and E, which I think you hopefully derived on an earlier problem set, and then plugging that into our formula for the differential cross-section. So for example, if you look in the textbook, there's some nice, lovely 3-line formula, 2-line formula for this differential cross-section as a function of the scattering angle for this E plus E minus annihilation process. Yes, question.
Maybe it's a question. Why didn't the traces of various matrices arise in the case of the vector field?
They did arise, of course, because you ended up calculating things like epsilon mu, g mu nu, propagator epsilon nu, okay, which you could write as a trace of epsilon nu star epsilon mu g mu nu, okay, right, where you view this as a 4x4 matrix and this is a 4x4 matrix. Okay.
But they are not used.
Well,
It's the equation of motion simplified.
yeah, I mean, you certainly could have done it this way. Okay.
Maybe in the case of complex.
No, I mean, I think that you certainly could have done it this way. Okay. If I remember correctly, when you did this photon scattering, the sum over polarization states. Yeah, I don't know. It depends how you did the problem. It was assigned on a problem set. I don't know how you did it. You certainly could have done it by writing it this way, and then using the fact that the sum over all polarizations of epsilon star epsilon was g mu nu. But you know, I guess, yeah. Maybe I should write this as m mu nu, okay, because it's some sort of scattering amplitude, right? But you certainly could have written it like this.
But here we just manipulate the identities so they cannot make the trace.
That's right, yeah. I mean, somehow, you know, when we write out vector indices, we tend to write out the indices completely explicitly. So you don't, I mean, let's put it this way. The traces, when you write out the indices explicitly, you don't need to write the word trace. Okay. I mean, you know, it's also just equal to that, right? I mean, you could write it as, if you want to write it in matrix notation, suppressing the indices, you would need to write something like this. Okay. Yeah. Oh, okay. Well, I still have 2 more minutes. Yeah. Okay. Yeah, don't worry. We'll be done. Yeah. Okay. Good. So, yeah, so certainly if you wanted to write things in an abstract notation with no vector index, then you certainly could have done that. Vector indices we tend to just write out explicitly. But you can't write out every index explicitly, or else you'll go crazy. Or, okay, so for example, we have this result for the scattering cross-section. Let me just quote the answer for you in one particular case. So rather than writing down the complete dependence on the scattering angle theta of the cross-section, let me just integrate it over theta and give you the total cross-section. So that's the integral overall d omega over all solid angles of d sigma over d omega. And it's 4 pi alpha squared, where alpha is 1 over 137. It's the coupling constant of electromagnetism, divided by the center of mass energy squared. And there's just a couple pieces of physics that I would like to point out about this formula. Okay. So the first piece of physics that you really want to notice is that the cross-section is proportional to the 4th power of the electric charge. Physically, that makes sense. As the electric charge increases, these particles will interact more strongly, and the probability that these 2 particles will interact and annihilate increases. And it's also inversely proportional to the center of mass squared energy. That also makes sense. If you take these electrons and you collide them together with greater and greater energy, then you know, at higher energy, there's a larger chance they'll just fly right by each other without even having a chance to interact. Okay, so next class, what I wanted to do is just consider a couple more examples. So there's the example of Rutherford scattering. That's basically the example you do on the problem set, and the example of Compton scattering. And that will really take us through kind of the basic processes in quantum electrodynamics. Okay? And so at the end of next class, we'll have a little more time, and I'll just sort of maybe spend a little time talking about the big picture, where we'll be going next semester, and where, you know, really what we've learned over the course of the class. Okay, see you on Tuesday. Thank you.